To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Now also I am going to discuss with you all the functions of a transistor. In the previous chapters we discussed what transistors are. They are electronic devices where there are two p-n junctions, therefore three terminals, and the terminals are base, emitter, collector. Always charge carriers flow from emitter to collector, and based on how the P and N type semiconductors are arranged, we have two types of transistors, the PNP transistor and the NPN transistor. So the symbol for the transistor is given where the arrowhead indicates the emitter and the direction of the arrowhead indicates the direction of the current flow. So thereafter in the previous chapter, we discussed the function of the transistor. We saw how the transistor functions as an amplifier. It amplifies current and it amplifies signals. Now we are going to look at another function of a transistor, that is the switching action of a transistor. Now you all are familiar with switches. Switches that are used in the electric circuits. That is normally the physical switch where you turn on and allow the current to flow and you turn it off and prevent the current from flowing. Similar to this, we can use transistors as switches in electronic circuits. So we are trying to understand that particular function of a transistor. Instead of a mechanical switch, so here you can see, instead of a mechanical switch, the transistor can be used as an electronic switch that operates according to a certain sensation. So when we say a sensation, it can be the light sensation, it can be heat. So depending on the sensation, you can use transistor as a switch. In electronics, when digital circuits are constructed, the transistor is often used as a switch. So in a digital circuit. So this is the introduction, students. So we can use transistor as a switch. Say you're familiar with lights or house lighting systems where automatically the lights are turned on when darkness falls. When the intensity of light outside or the environment decreases, the household lights come on automatically. So there is a sensor, we call it a sensor switch normally. So there a sensation is detected and then accordingly the circuit functions. To do that, we can use transistor as a switch. So that is what we will try to understand now. So the activity. Transistor as a switch. So these are the apparatus required for the activity. As you can see here, students, this is a transistor, the NPN transistor that we normally use. The transistor needed. So here you can see the serial number also. Then we need a multimeter. So that we can measure the potential difference. Then we need bulbs, small bulbs with 2.5 volt bulbs, like that we need a bulb. Then we need a battery cover. Into the battery cover we will be putting the dry cells. Then we need the volume controller. Volume controller or volume control resistor. Volume controller, you know, is a variable resistor. Then we need the fixed value resistor. Fixed value resistor. Then a circuit board. Then we need the connecting wires. and the switch. So these are the apparatus that are required for the activity. A transistor, multimeter, bulbs, battery cover, dry cells. Then we need a volume control resistor, fixed value resistor, circuit board, connecting wires and switch. So here we are going to observe the switching action of a transistor. Then I'll move on to the next slide where I discuss the activity with you all, the method of the activity. So here, method. Construct the above circuit on the circuit board. Rotate the volume controller to the extreme right so as to have the minimum resistance. So we'll look at the circuit first. Here you can see the NPN transistor and the terminals, emitter, base and collector. So here you can see base is connected to the volume control resistor. You saw in one of the previous activities, the terminals are numbered as 1, 2, 3 of the volume controller VR, and accordingly we need to connect it. So the base is connected to terminal 1. Then you can see the second terminal is connected to the emitter. There that is set to, that is a volume controller that can provide a 10 kilo ohm resistance. Then the emitter is connected to a switch, so that on the switch and see whether the circuit is functioning or not. Then here we have the dry cells, 3 volt batteries connected here. The negative terminal is connected to the emitter and the positive terminal is connected to the light bulb, 2.5 volt bulb, and then that is connected to the collector. And on this side, you can see the base collector terminals are connected with a 10 kilo ohm resistor. That is a very high value, 10,000 ohms resistance. So that is how we connect the circuit. Then here you can see the voltmeter. It's actually not the voltmeter. We are using the multimeter. In the multimeter, we set it to voltage and also the 2.5 volt range in the multimeter. And then we connect the terminals this way, where the positive terminal of the multimeter needs to be connected to the base. And the negative terminal will be connected to the emitter. That is how we connect the circuit. So then this is what we do here. Rotate the volume controller, I am reading it here. Rotate the volume controller to the extreme right so as to have the minimum resistance. Rotate the volume controller to the extreme right as to have the minimum resistance. So when we have the minimum resistance here, current can flow through this. That is why we reduce it to the minimum resistance. Connect batteries while keeping the switch S in the off position. Now switch is open means it's off. So when the switch is open, it is in the off position. We keep it in the off position and we connect the batteries. After doing that, select the multimeter range. Here you can see select the multimeter range, 2.5 volt direct current, and connect it between the base and emitter of the transistor. Its positive probe must be connected to the base. That is what I told you. Here we have the sign positive that has to be connected to the base, and the negative probe will be connected to the emitter. And the range is going to be 2.5 volt direct current. Is that clear? So that is how we connect the circuit. I will continue, move on to the next slide. So here also we have the same diagram. I have explained this to you all. Now here you can see. Now open switch S, observe the voltmeter reading and the lighting up and brightness of the bulb. Here there is a printing mistake, students. This should be close the switch. Close the switch or on the switch. Now close switch S, because when you close switch S only, the potential difference will give rise to a current flow. Then only you can see the bulb light. If the switch is open, we cannot see that. So now close or on switch S. Observe the voltmeter reading and the lighting up and brightness of the bulb. So that is what you are going to observe. Turn the volume controller gradually to the left so as to increase the resistance. So we are going to turn the volume controller gradually to the left as to increase the resistance while observing the voltmeter reading and the bulb. So earlier we turned it to the right so that the resistance becomes the least, the lowest value. And then only we close the switch, we observe the bulb. Now what we do is we try to increase the resistance by rotating the volume controller. At the same time, you have to look at the bulb and the voltmeter. Observe that the bulb begins to light up when the voltmeter reading is about 0.7 volts. So until this comes to 0.7 volts, from the lowest value to 0.7 volts, but when the multimeter, that is the voltmeter reading, shows 0.7 volts, then you see the light come on, the bulb will light and it will be with less brightness. But when you keep on adjusting the volume controller, increasing the resistance, the brightness of the bulb will increase. And between the range 0.7 to 0.8 volts, the maximum brightness will be reached. So there below 0.7 volts, you will not see the light come up, and from 0.7 volts, you will see the bulb light, and until 0.8 volts it's reached, the brightness will increase. That is what you will observe. So observe that the bulb begins to light up when the voltmeter reading is about 0.7 volt, and the bulb has the maximum brightness when the voltage is about 0.8 volts. So you have to remember these values. Begins to light up when the voltmeter reading is 0.7 and maximum brightness when the voltage is about 0.8. So that is how we do the activity. And remember, when we turn on the switch, close the switch and observe while adjusting the volume controller, increasing the resistance only, you will see the bulb light and the brightness will increase gradually. So this is the activity, students. Now we will do it in the lab to understand the switching action of a transistor. Okay, students. So now I am going to do this activity in order to observe the switching action of a transistor. So to do this activity, these are the materials that are needed. This is the circuit diagram given in your textbook. I have made slight changes, or actually I have not used some of the components shown in the circuit diagram. Now we will try to understand how it has been connected. So here in the middle you can see a transistor. From the direction of the arrow, you all know this is an NPN transistor. So here also we have an NPN transistor. Then this side there is a switch, but here I have not used a switch. Directly I have connected it to the dry cells. So here you can see two dry cells, 3 volt potential difference. So two dry cells have been connected. And then here you can see to the collector there is a light bulb connected, but in the circuit I have used an LED. So this is a circuit that has an LED connected. So transistor, light bulb and LED. Then on this side you can see that there is a fixed value resistor. That is here you can see the fixed value resistor connected there. And here you can see a volume control resistor, a variable resistor, volume control resistor. That is what I have connected here. So to this terminal I have connected a volume control resistor. In the activity, we are supposed to use a voltmeter in order to measure the potential also. That I am not going to do in this activity. So these are the components. Now what we will try to do is, first we need to have the volume controller turned extremely to the right side. Now here you can see I cannot turn it anymore. I have turned it extremely to the right side. Then of course the resistance is very less. So when the resistance is very less also, there is no current flowing through the transistor. So that is why the bulb does not light. Here you can see the bulb does not light. So now what I am going to do is I am going to turn it to my left side, like a clockwise rotation, turn it towards the left side. Then you all have to observe the LED connected to the transistor. Now when I rotate it like this, when I am rotating it, you all look at the LED. Can you see there's a dim light there? When I keep on increasing it, at the maximum point, you can see there the LED lights up brightly. Now what happens is, when I increase the value of the resistance here, the volume control resistor, the potential difference between base and emitter reaches a value of 0.7 volts. At that point, there is a current that flows through the emitter collector circuit, and the bulb or the LED here is connected to the emitter collector circuit. So there is a current flowing through the emitter collector circuit, and because of that the LED lights. When we increase the resistance using the volume controller, the potential difference reaches a value of 0.7, and at that point the transistor acts as a closed switch at the on position, and there a current flows through the collector, and because of that the bulb lights up or the LED lights up. Again when I turn it back, now you saw LED has gone off. The reason is when we decrease the resistance, the potential also decreases. Because of that, there is no current flow through the collector. So then there is no light on. The LED does not light. So here you all can understand, students, by adjusting the potential difference or based on the resistance of the volume controller, the potential difference across the base emitter circuit changes. Based on that, the light comes on and it can be turned off. So if we design a circuit where the potential difference can be changed above a certain value, in this instance 0.7 volts, and below 0.7 volts, then this particular circuit with the transistor can be used as a switch. Below 0.7, that is between base and emitter, it is switch at the open position, switch off. 0.7 and above, it becomes a closed switch and the bulb comes on. So that is how the transistor acts as a switch. Okay, students. So you all were able to observe the activity clearly. Now in the lab, you can remember I did not use the voltmeter. Now in this activity, in the diagram, the circuit you can see there, students, there is a voltmeter attached between the base and the emitter. But in the activity, we did not use the voltmeter or the multimeter which was set to voltage 2.5 volts. We did not use that. But you were able to see when I change the resistance using the volume controller, at one point the bulb lights and then the brightness increases and reaches a maximum. And when I again change the resistance, you did not see the bulb light. The bulb goes off. So that was the observation you all were able to get. So we will try to understand how the transistor acts as a switch to turn on the light bulb and to turn off the light bulb. Now look at the circuit. We have the 3 volt battery here, the potential difference, and here we have the switch. Now when we close the switch S, then only the circuit will be complete. So that is for our practical application. But the transistor is going to act as the switch. That is why even when S is closed, at one point you don't get the bulb light, but thereafter you get the bulb light. So you have seen that. So what happens here? Now let's say S is closed. I will use a color, blue color. So S is closed. And then what do? We have the fixed value resistor here. Current has to flow this way. And we have the volume control. We change the volume control knob, right? You can see here, we change the volume control knob. If you want, we can go back to the previous activity. Here you can see, initially what do? We rotate the volume controller to the extreme right, so as to have the minimum resistance. We have the minimum resistance there. When the resistance is minimum, now I will explain it here. When the resistance is minimum here, what do you think will happen? The current will flow. Now let's say minimum resistance in volume controller, right? So what will happen? There will be current passing this way. Then current flows this way. Current can flow through the 10 kilo ohm resistor. And then, now here there is a resistance for the transistor, but the volume controller has the minimum resistance. So because of that, the current chooses to flow through the least resistance path. So here it is going to be the external circuit that will have the lowest resistance. Because of that, there will be no current flowing through base. Instead, current flows this way through the external circuit. So then what happens? There is no current flowing through the base of the transistor. Therefore, there is no current flowing through the collector. No base current, no collector current. So that means the transistor acts as an open switch. You have to remember that. So minimum resistance in volume control resistor. Therefore, current flows through the external circuit as shown, that is by the blue color arrow, as shown, without flowing through the transistor. Then the transistor acts as an open switch. So that is one instance. Then what do? We increase the resistance of the volume controller. I will use a different color for that. The resistance of the volume controller is increased. Then what happens there? There, if we look at the circuit, now also this switch is closed, the circuit is completely connected, then there will be current flowing this way, starting from the positive terminal of the battery, flows this way also. But at this point, now we have increased the resistance of the volume control. So what happens is, the resistance of the external circuit is now greater than the transistor. So because of that, When the voltmeter reading shows a potential difference of 0.7, there will be a base current flowing. Current will flow through the base. So, when there is base current flowing, there will be a collector current also flowing through it. So, because of that, the bulb will light, but the brightness will be less. If you keep on increasing the volume controller until the potential difference becomes 0.8 volts, what will happen is the base current will increase, therefore the collector current will also increase, and that will increase the brightness of the bulb. And in this instance, above 0.7 volts, the transistor acts as a closed switch and current flows through the transistor. A base current flows, so you all know if a base current flows only, a collector current will flow. So now the current is flowing through the transistor like that. Collector current, base current. So transistor acts as a closed switch. That is how the bulb lights. Is that clear, students? So we have to write that explanation here. The resistance of the volume control is increased, then current flows through the base of the transistor. That is IB. Therefore, a current flows through the collector. That is IC. Since IC flows through the bulb, it lights. So that is what you need to understand. So very important, below 0.7 volts, transistor is an open switch, and above 0.7 volts, transistor is a closed switch. So you can consider this as a note. I'll be discussing the same thing again also, but for you all to understand now. Is this clear, student? So if we quickly go back and have a look at the activity. So here you can see we have to close S, that is to make the circuit complete. Then what will happen? From the battery, current flows, but since the resistance of the volume controller is the minimum, the external circuit will have the lowest resistance. Because of that, current flows through the external circuit. That is what is indicated by the blue color arrows. But when you increase the volume controller, then what happens? The resistance of the external circuit increases, and when the voltage or the potential difference is 0.7, you can see there will be a current flowing through the base. That is the IB current. That is shown by the black color arrow. So when there is current flowing through the base of a transistor only, there will be current flowing through the collector. This is an NPN transistor. So the current flows from collector base to emitter. So because that IC current, the collector current flows through the light bulb, the bulb will light. Can you all understand that? So that is how the transistor functions as a switch. So if we read the second part of the explanation, I have already discussed this with you all. The resistance of the volume controller is increased, then a current flows through the base of the transistor, that is IB. Therefore, a current flows through the collector, that is IC. Since IC, that is the collector current, flows through the bulb, it lights. So here you have to remember, below 0.7 volts, the transistor is an open switch, and above 0.7 volts, transistor is a closed switch. And when the potential difference is about 0.8, the brightness will be maximum. Is that clear, students? So that is how the transistor functions as a switch. So with that, we will move on to the next slide. So here you can see we can draw the following conclusions from the above activity. And these, some of them I have already discussed with you all. Like I told you all, below 0.7 volts, the switch is open or it is closed. The transistor does not allow to current flow through the bulb. Therefore, the bulb does not light. So the transistor acts as an open switch when the potential difference is below 0.7 volts. But as the potential difference reaches a value of 0.7 volts, the bulb starts to light. The brightness is less, but still the bulb lights up. So that means the transistor starts acting as a closed switch. Thereafter, up to 0.8 volts, the transistor is a closed switch. Or we can say below 0.7 volts, the transistor is an open switch, and from 0.7 up, the transistor acts as a closed switch. So that is how the transistor acts as a switch in electronic circuits. Now here, if we look at the conclusions, we can draw the following conclusions from the above activity. The first one you can see, when the voltage difference between the emitter and the base is less than 0.7, because we connect the voltmeter between the emitter and the base. So you can see here, voltage difference between the emitter and the base is less than 0.7. There is no collector current IC. When the voltage difference between the emitter and the base is about 0.7, the collector current begins to flow. So this is the second conclusion. And when the voltage difference between the emitter and the base exceeds 0.7 volt, the collector current reaches a maximum. So all are very important conclusions. So therefore, this is how the transistor acts as the switch. Therefore, when the voltage difference between base emitter terminals is less than 0.7 volts, the transistor acts as the open switch. And the voltage difference between the base emitter terminal exceeds 0.7, it acts as a closed switch, or it is in on position. Is that clear to you all? So here, by using the volume controller, by adjusting the resistance, we are controlling the current flow by changing the voltage across the base emitter terminals. So when the voltage is below 0.7, the transistor is an open switch. It's in the off position. When it is 0.7 and above, the transistor is a closed switch. That is, it is in the on position. So that is how a transistor acts as a switch. But the same circuit, now we said based on a sense. Sensing something, I said either it can be light, heat or different sensors. Using that, we can use the transistor as a switch. So that is what we will be discussing after this. With that, I'll move on to the next slide. Let us engage in the next activity to demonstrate how to design a switch circuit that automatically lights up when darkness falls. So, a switch circuit that automatically lights up when darkness falls using the above principle. So, here we will use a light dependent resistor LDR as the light sensor. So, here we will be using an LDR as the light sensor. Now, we have seen and used and you know about LDRs, light dependent resistors. What do? They have very high resistance when there is no light incident on it. In the dark, when there is no light incident on the LDR, the resistance is very high. But as the intensity of the light that falls on the LDR increases, the resistance decreases. So, it can act as a light sensor. When it is dark or no light, the resistance is high. When there is light incident on it, the resistance decreases. So, that is how we are going to use it as a light sensor. When light is incident on its front surface, its resistance becomes very low, of the order 1 ohm. While in the dark, it has a very high resistance of the order 10,000 ohms. So, that is how we use it as a light sensor. So, now we will go to the next slide where we try to understand how this can be used as a circuit. So, activity demonstrate how to design a switch circuit that automatically lights up when darkness falls. So, the apparatus that are required. We need the transistor. We need the LDR, light dependent resistor. Then we need the volume controller. Then we need the light bulb. Then it is the battery cover. We need a circuit board and connecting wires. So, the transistor, light dependent resistor LDR, volume controller, the light bulb, battery cover, circuit board and connecting wires. These are the apparatus that are needed to do this activity. Switching action of a transistor but with light sensor. So, it acts as an automatic switch. So, we will look at the method in the next slide. So, then method. To understand the method, students, first we will understand the circuit given here. So, look at the circuit there. Now, you can see this is the transistor given to us, D400 or D313, one of the transistors can be used. So, here you can see when you look at the symbol, it is an NPN transistor because the arrow points towards the outside. And anyway, you all know for our activities, we will be using only NPN transistors. So, emitter, base and collector. Then you can see the emitter is connected to the negative terminal of the battery, again NPN transistor, and a 3-volt battery is used there. The positive terminal is connected to the collector. And there you can see a light bulb is connected. In addition to that, you can see here between the collector and the base, there is a volume controller. Volume controller is a variable resistor. The maximum resistance is 10,000 ohms or 10 kilo ohms. Then you can see the terminals 1, 2 and 3. They are labeled here. So, terminal 1 is connected with the bulb and here on this side, the terminal 3 is connected to the base. That is how we connect the volume controller. You can remember that. Then here you can see this part. between the base and the emitter, we have an LDR. LDR is the light dependent resistor. You all know the function of a light dependent resistor. What is that? When there is no light incident on it, the resistance is high. So because of that, it doesn't allow current to flow through. But when there is light falling on it, then what happens? The resistance decreases, and because of that, it allows the current to flow through it. That is how the LDR functions. So this is the circuit that has already been prepared. Now we will look at the method. Here you can see, cover the top surface of the LDR from light with your fingertip and adjust the resistance of the volume controller until the bulb lights up. So you have to cover this and you have to adjust the volume controller until the bulb lights up. Remove your fingertip and allow light to fall on the LDR. Then you remove the covering. Either you can cover it with your fingertip or you can close it with a cloth or a piece of paper, anything. As long as light is not incident, you adjust the volume control and observe the bulb light. Then what we do is we take off the covering so that light will be incident on the LDR. Then only you will see what happens in the circuit. There, of course, you will understand that the bulb will light up. Now here students, although I am going to do the activity in the lab, before I do that, I am going to explain what happens in this circuit. Then you will have a better understanding as to how to observe and get the understanding of the observation. So this is what will happen. Initially, when the LDR is covered, there is no light incident on it. So because of that, there is going to be a large amount of resistance. When there is no light incident, the resistance of the LDR is high. So because of that, what will happen is the resistance of this external circuit is going to be high. At the same time, now current flows this way, again to this point, up to here. We will have to adjust the volume control so that the bulb lights. So accordingly, this resistance will change so that there will be current flowing up to this point. Now when it comes to this point, now LDR has high resistance. When no light, high resistance. So because of that, current will flow into the transistor through the base. So when there is current flowing through the base, what will happen? Automatically, there will be a current flowing through the collector. Only when there is a base current, there will be a collector current. So because there is a collector current flowing, the bulb will light. Is that clear? So that is when the LDR is covered. So I will write that explanation first. When LDR is covered, there is no light incident on the LDR, then its resistance is high. Because of that, the current flows through the base of the transistor. So we call it the IB, base current. Then there will be current flow through the collector, that is IC. Since the IC flows through the bulb, it will light. It will light. So the transistor acts as a closed switch when it is dark or no light on LDR, and the bulb lights. So night time the lights come on automatically. Why? The transistor acts as a closed switch. At the same time, if we go back, here you can see I will use a different color now. Now let's say light falls on LDR. Then what happens to the resistance? Resistance less. Resistance low. Then what will happen? Again, the current flows from the battery this way up to this point, and it can flow through the volume control resistor. But now the resistance of the LDR is less compared to the resistance of the transistor. So what will happen? There the current will flow through the LDR, then through the external circuit back to the battery. So there will be current flowing through the external circuit only. There is no current through the base of the transistor. And if there is no current flowing through the base of the transistor, will there be current flow through the collector? No. There is no current flow through the collector. So then the transistor acts as an open switch and the bulb does not light. That is what the second step says. Remove your fingertip and allow light to fall on the LDR. Then you will see this light will go off. Bulb will not light. That is because the transistor acts as an open switch. You have to remember that. So here we have to say, when light falls on LDR, the resistance decreases and current flows through the external circuit and not the transistor. Therefore, the bulb does not light. The transistor acts as an open switch. So in this circuit, what is the function of a transistor? The transistor acts as an automatic switch with a light sensor. The light sensor is the LDR. When light falls on the LDR, that is the daytime, the transistor is an open switch. So the lighting system will be off, the bulb is off. But during the night time, when there is no light falling on the LDR, then of course the transistor acts as a closed switch, current flows through it and the bulb lights. So if we have this system in the household, then also that will be the case. Automatically, as dark falls, the lights of the household will come on. Whereas during the daytime, automatically the lights will be switched off. So even in street lights, we can use this circuit. You all have to remember that. So here, if we quickly read this, when light falls on LDR, the resistance decreases and current flows through the external circuit and not the transistor. Therefore, the bulb does not light. The transistor acts as an open switch. Is that clear, students? So that is the explanation for this particular circuit, and this is the activity. So here you can see I have explained what will happen when we use this circuit. I'm sure you all have a good understanding about that. So now let's go to the lab and do the activity. So while you all observe what happens, just recall what I have explained to you as well. Okay, students. So now I am going to do this activity to show you all or to understand how a switching action works, that is an automatic switching circuit. Now when there is no light, now say during the daytime we don't need the lights on. But as night falls, when darkness increases, we need the lights to come on automatically. So there it is an automatic switch circuit using the transistor. For that, this is how we are going to have the circuit. Again, here you can see it is an NPN transistor that we need to use. Now here you can see the base emitter terminal is connected to an LDR. So if you compare this circuit diagram with the circuit given here, you can see this is the NPN transistor. You all can see the NPN transistor here, that is this. Then here you can see the base emitter is connected to the LDR, light dependent resistor. So this is the LDR, light dependent resistor. Then here if you look at this part, we have a variable resistor, but instead I have connected a fixed value resistor, 10 kilo ohm resistor. So that's a 10 kilo ohm resistor. Then here you can see it is a light bulb. Now instead of the light bulb, I have a light emitting diode there. So you can see instead of a bulb, we have a light emitting diode there. Then on this side, here you can see there is a 3 volt potential difference applied between the emitter and collector. For the emitter collector circuit, a 3 volt voltage is applied. So that is given by the batteries. So the same circuit, a similar circuit where instead of a bulb we have an LED, and instead of a volume control resistor, that is a variable resistor, I have a fixed value resistor here. So then if we look at the function of this circuit, now first recall the function of an LDR, light dependent resistor. When there is enough light falling on the light dependent resistor, the resistance is very, very low. When there is no light falling, or the intensity of light falling on the LDR decreases. The intensity of light decreases, the resistance increases. So when there is complete darkness, the resistance of the LDR is very high. So as it is, if you look at the circuit, now there is light falling on the LDR. So what happens is the LED does not light. The reason is there is current flowing through this external circuit, not through the transistor. When there is light falling on the LDR, the resistance is very low, Because of that, there is current flowing through the LDR but not through the transistor. That is why there is no current flow through the bulb or the light emitting diode LED here. But if I cover the LDR, now if I cover it, you can see the LED light up. What happens here? I have covered the LDR completely, so the resistance of the LDR has increased. Because of that, the current does not flow through the external circuit. Instead, current flows through the transistor. Through the base, there is a current flow. That is why the LED or the bulb lights up. So, when there is darkness, LDR is sensitive to that. Resistance of the LDR increases. Because of that, a current flows through the transistor and the bulb lights up. So, that is what happens. Now, let's say the intensity of the light decreases gradually. If I slightly cover the LDR, now can you see the LED? The intensity is less. Now, as I show more light, the LED goes off. If I cover it slightly, you can see a small light, more light, and when it is completely covered, you can see the brightness of the LED. So, can you all understand that? As the intensity of the light in the environment outside decreases, there will be more current flowing through the LED, or according to this the bulb, and the intensity of that light will increase. So, this particular circuit acts as an automatic lighting switch circuit. Can you all understand that, students? Okay, students. So, now what I will do is, without covering the LDR with my hands, I will switch off all the lights in the lab so that you will be able to see the LED lighting up. So, now students, can you all see the light bulb? The same circuit, I haven't done any changes. I am not covering the LDR, but the light in the room inside the laboratory is less. So, you can see the LED has lit up and it is a very bright light. So, that is how the automatic switching circuit functions. So, with that, students, you all were able to understand when all the lights in the lab were switched off, you were able to see the LED light up. So, that is how an automatic lighting circuit functions. When the dark falls or the intensity of light in the environment decreases, automatically there is current flowing through the transistor and that turns on the LED or the light bulb that is shown in the circuit diagram here. That is the function of a transistor as an automatic switch. Light sensitive automatic switch. Okay, students. So, you all saw the activity, but did you all observe? Did you all observe clearly? I am sure you did. So, when I closed the LDR, there was no light incident on it, and then you were able to see the bulb light. But when I removed the hand from the LDR, when there was light falling on it, you saw that the bulb goes off. So, from that, you all were able to understand that the transistor acts as a sensor switch, an automatic switch that senses light. When there is light in the environment, the transistor goes off, or the transistor acts as a closed switch. That is why the bulb goes off. And when there is no light falling, then the transistor acts as a closed switch, or it is a on position. Then of course the bulb lights up. So that is how the transistor acts as a switch with a light sensor. I am sure you all can understand that. So if we write down the observation, when there is no light falling on the LDR, the bulb lights. When light falls on the LDR, the bulb goes off, or we can say does not light. So that is the observation. From that, what can we conclude? Can say conclusion. When light is not incident on the LDR, then its resistance is high. The transistor acts as a closed switch, that is on position. That is why the bulb lights. When light is incident on the LDR, the resistance is low. Then the transistor acts as an open switch. That is the off position. Therefore, the bulb does not light. So here the transistor acts an automatic switch. With the light sensor. So that is how we use the transistor. So here if I go through this quickly. Now this is what we were able to observe. When there is no light falling on the LDR, the bulb lights, and when light falls on the LDR, the bulb goes off or it does not light. So from that we can get this conclusion. When light is not incident on the LDR, then its resistance is high. The transistor acts as a closed switch, that is it's in the on position, and that is why the bulb lights. At the same time, when light is incident on the LDR, the resistance is low. Then what happens is the transistor acts as an open switch or it is in the off position. Therefore, the bulb does not light. Here the transistor acts as an automatic switch with light sensor. Like I explained to you all, like you all saw during the activity, you can remember when there is no light incident on the LDR, the transistor acts as a closed switch, so the bulb lights. When there is light falling on the LDR, the transistor acts as an open switch and there is no lighting of the bulb. So here transistor acts as an automatic switch with a light sensor, and the light sensor is the LDR. So when I explain the method to you all, I have already explained the function of the circuit. Just to have a look at that, I will go back to the previous slide. There you can see. Now this is the explanation I gave you all. When there is no light on the LDR, the resistance is high. So because of that, the current, the blue color arrow you can remember, current flows through the base of the transistor. Because of that, there is a current flowing through the collector and the bulb will light. But when there is light falling on the LDR, that is the pink color arrow, you can see the resistance is less. Because of that, the current flows this way, but current does not flow into the base of the transistor. It flows through the LDR and back to the battery. So it is an current flowing through the external circuit. At that instance, the transistor acts as an open switch. So the bulb does not light. So when there is daytime light falling on the LDR, bulb does not light. But when dark falls and no light is incident on the LDR, transistor acts as a closed switch and the bulb lights. That is how the transistor functions as an automatic switch. So like I mentioned to you all before, we can use this system in the household where the lights can come on automatically when dark falls, or in the street lights we can use this system. When it is dark, the street lights come on, and then if it is daytime, the street lights go off. So wherever we need an automatic switching system related to a light sensor, we can use this circuit. I'm sure you all can understand that. So then I'll move on to the next slide. Here I have already given the observation and the conclusion of the activity. Just to further understand what is happening by using the LDR, I will move on to the next slide where we have an extra knowledge component and we will try to understand that as well. Here we have an extra knowledge component given to you all. In the activity 11.6, that is the previous activity where we use the volume control and the LDR. So there you can see the volume control VR acts as a variable resistor and the LDR as a potential divider. When we say potential divider, it divides the potential difference of the bulb between the emitter and collector. So that is what is shown here. You can see base is in the middle, here voltage 0 and there voltage plus 3. It is dividing, the LDR is dividing the potential. In the activity 11.5, instead of the volume control, we use the 10 kilo ohm resistor and 10 kilo ohm variable resistor instead of the LDR. So there also we had the resistor as a potential divider. The total potential drop across the two resistors is 3 volts because we supply a voltage of 3 volts. So when we have V equals IR from Ohm's law, 3 is the potential, 3 volts. It's equal to I. Here both the resistors, if you look at it, they are connected in a series manner. So R1 plus R2 is the equivalence resistance. Therefore, I is equal to 3 divided by R1 plus R2 when you rearrange the equation. If the potential at B is base, is VB, voltage base. The potential difference across R2 is VB. R2 is this. Here is the base, so potential is VB. So VB, that is potential at the base, is equal to R2 into current I. Why here we have got the equation for current I, 3 divided by R1 plus R2. If we substitute that here for the base potential VB, R2 into 3 over R1 plus R2. That is how you get the equation. I'm going to continue this in the next slide. So, by keeping R1 constant, we adjust the volume controller, we keep it constant. So, R1 is constant. And varying R2, how do we vary R2? By changing the light incident on R2, because R2 is LDR. Any potential from 0 to 3 volt can be given to that point. So, you can change the potential difference. If the resistance is 0, then the potential is also 0. Why? V equals IR. When R is 0, potential becomes 0. So, like that, we can change it between 0 and 3 volts. If R is equal to 10 kilo ohm, the value of R2 in order that V is equal to 0.7 volts. You all know for the transistor to function, we need at least 0.7 volts. So, voltage 0.7 volts, 3 into R2 divided by 10,000 plus R2. That is if R is 10 kilo ohm. How do we get this equation? 3 into R2 divided by R1 plus R2. Here we have this. This R1 is what we have as 10 kilo ohms. That is 10,000 ohms. So, when you substitute that here and you rearrange the equation, you take it to the other side. So, it becomes 7,000 plus 0.7 R2. That is equal to 3 into R2. Again, you rearrange. 7,000 equals 3 into R2 minus 0.7 R2. Then that is equal to 2.3 R2. So, from there, if you calculate R2, 7,000 divided by 2.3, you will get the value as 3043 ohms. So, therefore, when R2 is 3043 ohms, the potential at base, that is B, becomes 0.7 volts. When the resistance of the LDR increases up to 3043 ohms. When the resistance of the LDR increases up to 3043 by decreasing the light incident on it, the bulb dimly lights up. The bulb dimly lights up. And when the light is further decreased, the potential increases up to 0.7 volt and the current IC increases to a maximum. At this point, the switch opens. This is a mistake, students. This should be switch closes. Then only the bulb will light. If the transistor acts as an open switch, then the bulb will not light. So, here the potential increases and the current increases to a maximum. And that is when you have the maximum brightness of the bulb. So, that is when there is no light incident on it. So, when the resistance of the LDR increases up to 3043 ohms by decreasing the light incident on it. So, we need the bulb to light up when there is dark. When there is no light falling on the LDR, there is darkness. During darkness, the light has to come on automatically. So, then the transistor should become a closed switch. So, that is the action here. These are things that you need to just understand, students. This is for extra knowledge where you need to understand what happens. By changing the resistance, we can change the transistor to act as an open switch and a closed switch. So, that is why it acts as an automatic switch. So, that is the switching action of a transistor. So, with that, students, I have completed this lesson. In the next slide, I am going to discuss the summary of the lesson with you. So, summary. The charge carriers that conduct electricity in metallic conductors are the negatively charged electrons. So in metallic conductors, it is only the negatively charged electrons. Metallic conductors, negatively charged electrons. But in semiconductors, what do we have? We have both electrons and holes. So that is both negative charges and positive charges corresponding to a positive charge. That is, the holes are corresponding to a positive charge, act as carriers that conduct electricity. If I read that again, in semiconductors, both electrons and holes corresponding to a positive charge act as carriers that conduct electricity. Since a hole is formed in a semiconductor, when a bond breaks, releasing an electron, the number of free carrier electrons in the semiconductor is equal to the number of holes in it. So that is something you all know, that is the intrinsic semiconductor. Due to heat energy, there is breaking of bond and there will be free electrons and holes, but the number of holes will be equal to number of electrons. Therefore, when a potential difference is applied across a semiconductor, holes move from positive to the negative potential, while the electrons move from the negative to the positive potential. So that is also something you all know. Holes are positive charges, so they move from positive to negative. Electrons move from negative to positive. And the standard current flows from the positive to the negative potential. Then, an N-type extrinsic semiconductor. So, you are familiar with N-type extrinsic semiconductor. The previous one is intrinsic semiconductor. Extrinsic is produced by doping the semiconductor with a group 3 or group 5 element. When we dope it with group 5, you get the N-type semiconductor. So, an N-type extrinsic semiconductor can be formed by doping an intrinsic semiconductor with a group 5 element. Then a P-type extrinsic semiconductor can be formed by doping an intrinsic semiconductor with a group 3 element. So, you all have to understand these also. We have discussed all these from the beginning of the chapter. I am sure you all can remember all what we discussed. So, when an external potential difference is applied across a PN junction so as to make the P region negative, the depletion region broadens and no current flows across the junction. That is known as reverse biasing. You connect the P to the negative terminal and N to the positive terminal. The depletion layer becomes broader and it is reverse bias. That the PN junction is reverse bias. So, no current will flow through it. I'll move on to the next slide. When an external potential difference is applied across a PN junction so as to make the P region positive, the depletion region thins down, and if the external potential difference is sufficiently large to make the potential barrier, then a current flows across the junction. This is known as forward bias. So, when we properly connect the terminals, P junction is connected to the positive terminal, N junction is connected to the negative terminal, what happens? The potential barrier becomes thinner and thinner. And if you supply enough potential, now we all know for a silicon diode, the potential barrier is 0.7 volts. For a germanium semiconductor PN junction, it is 0.3 volts. So, you need to provide a potential difference more than that. So, then what will happen? The potential barrier will be overcome. And then there will be a current flowing through that. That is what is known as forward bias. Diodes can be used for the rectification of an alternating current. So, we have discussed that also. Rectification of an alternating current. The potential barrier across a PN junction for a silicon junction is about 0.7 volts and for a germanium junction is about 0.3 volts. Since charge carriers in a P-type semiconductor are holes corresponding to a positive charge, in a PNP transistor, the current flows from the emitter to the collector, inward arrowhead. This is something that we discussed and you all have to remember, students. Since charge carriers in an N-type semiconductor are electrons, In a NPN transistor, the current flows from the collector to the emitter. That is outward arrow. Is that clear, students? So, in a PNP transistor, the arrowhead is inwards. And in an NPN transistor, the arrowhead is outwards. And usually we use the NPN transistors for our activity. Always carriers flow from the emitter to the collector. That's important. Always carriers flow from the emitter to the collector. A transistor can be used as a simple current amplifier, signal, that is AC current amplifier, and a switch. So, those are the functions that we discussed in this and the previous chapters. So, I am sure, students, with all the discussion up to now, you all have a good understanding about semiconductors, diodes, the PN junction diode, the function of a diode as rectifiers, alternating current to direct current, and also how we can use it to protect devices from getting damaged due to wrong connection of terminals, incorrect connection of terminals, and also about LEDs and solar cells. Then we discussed transistors and their functions. I'm sure you all have a clear understanding of all these electronic devices. So with that, students, I'm going to end this chapter, and in the next chapter, I will discuss the questions given in your textbook. So I'm sure you will answer those questions by yourself first, and then you will listen to my discussion.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.